items in document of Newton's meeting.
Good afternoon, everyone. Thank you very much for the organizers. I'm very happy to be here, and it's my great honor to give a talk today here. This is a joint work with Jarek and Tio and Takoyaki. During my time as a postdoc in Oslo with my Professor Tio. Here's the background. So tonight, firstly, I will talk about some background. Then I will say what's my problem. Then I will introduce what's the result. Let's see, this is a very famous theorem, Schroeder theorem. It says that for any quadratic function, with two different roots, alpha1 and alpha2, and you iterate the function, apply the Newton method of this function f, and let R be the perpendicular bisector of this segment of two roots. Then this R will divide this complex plane to be H1 and H2, two half planes. So then that's we know for if you choose any points in this H1, then orbits will converge to root alpha1. If you choose any point in this subplane H2, then the orbit will go to alpha2. But when you are on this 9 then the orbit will not converge to either alpha1 or alpha2. And it's very complicated when you are on this L. The dynamic is very, very complicated. So this is the Newton method, and it's very popular. It also have many applications. So some of the applications like solving some system equations and also some optimizations. So let's say this is a application that's about new Newton method. So the goal is if we want to find minimum of capital F of this from R2 to R. So how you do is if you apply, so if you want to find the minimum of capital F, so you need to minus that. This is your Newton method, right? So then now you want minimum of capital F, so you will change this guy to be Z minus that you need to find the gradient. When the gradient equal to 0, right? And then here F becomes this. You want to find the root of small f. Now, if you want to apply to this problem, then the small f will become the gradient of capital F, and the f prime will become the hashing of the capital F. But then you cannot iterate this directly because your hash might be not invertible. So what to do is here, they add a little bit of term over here so that make sure all your hashing is invertible. Okay, but then there's another problem that sometimes your hashing might have some eigenvalues selective, some positive, so then you might have meet some set point. So what to do is we change the so then you see you calculate this new metric of your hashing, and this you have calculated the eigenvalues and eigenvectors, and then what you do is you change the sign, the negative eigenvalues to be positive. So then instead of iterate here, then you iterate zk minus wk. So this is how you choose that iterate your function like this. Okay. Well, then later there's a backtracking Newton method. So the difference between this backtracking Newton method and the previous Newton method is here, this step. Here is just that this minimum spectral is the minimum eigenvalue of this metric. So we choose delta J such that this guy is the minimum, the absolute value of minimum eigenvalues is bigger than this. So why? Because sometimes your eigenvalues can be very small, then your inverse of it then it become very big. So then your WK might get very big. So that's not, we don't want it. So then here's add a little bit restriction here. And the other difference is here, that the function values getting shrinking in a certain speed, not too small, not too slow. So then instead of iterate that zk minus wk, here you iterate zk minus gamma wk. Well, here is actually come a little bit from this random dumped Newton method. But I'm not going to talk about these two algorithms, how good are they compared with Newton method. What I'm going to talk is this. Let's see some experiments. So that we see here that for this function, if it's degree 2, you have roots. One root is around here, the other root is here. So if we apply this backtracking Newton method, then we have very similar picture like Newton method. So you choose any points, start initial point in this blue area, it will contract to one root, and on the other hand, the other side they contract to the other root. On this line, this is very like this perpendicular sector of these two roots. So this is for degree, if your f is the quadratic function. About if you're degree 3, higher degree, you apply for, so you know that for higher degree, if you use Newton method, you will get like for this function, give example, let's say this one, you have 3 roots, and each color instead of one basin of the root, and then you see that this is very typical that you have fractals on the boundary. But if we apply the backtracking Newton method, then it's different, that the boundary looks very smooth. So this is the experiment's picture shows this. So if yep.
Because it's impossible to guess the scale on this picture, could you point where I on this picture is? But approximately, obviously. Is it like in the middle of the yellow strip, or is it close to the border?
This is I.
So the size is 10. Do I see correctly? The size of the square.
It's minus 10 to minus 10 is just a bit part, yeah.
Yeah, I could see 0, but not 10.
One more question. So you say it looks smooth, but can you prove that it is?
That would be our.
Okay.
They are very so rigorously prove if it is really smooth or not. This will be this is the project we're doing now. Well, okay. So now so to be easier to figure out what's going on, this method, let's ask a simple question for polynomial degree 2. Start here. It will be more easier, I think. So the question is to ask, can we have similar results with Schroeder theorem for B and Q method for any of quadratic function f? So how to solve this problem. So we know that when you prove the Schroeder theorem, that you know that the dynamics of any function f, quadratic function, actually you can conjugate it to fz equals z squared plus some constant c. So the idea is very similar, so that what we want to do is if we change the coordinate, because the method is very complicated for backtracking Newton method, you always have to remember the metric of the hashing is changed because we added a little bit terms to make sure the hashing is always invertible. But in here, that because it's different, so then the idea is we want to show that for any quadratic function, if we can reduce it to consider fz, square minus 1 or plus 1 is fine, doesn't matter. So if we can reduce any of complex quadratic function to consider this one to different roots, so then then will be easier to say that. Well, so let's see, we have the first theorem that this method is invariant under R5 changeable coordinate. So it means that you on this fz, capital F. So if you change coordinate to be g of w, you net z equals aw plus b. Let's say this is the L of w. So what's this mean? So see this w, backtracking of g, if it's z, okay. So then question to ask if this is commutative each other. So this is not exactly conjugate like in Newton method, because that is easier that you just calculate because your function, you iterate this is fixed. They don't change. But in here, backtracking Newton method, you every time change because your delta change. And every time you iterate if you have negative eigenvalues, you will change it to be positive. So you want to prove this one. This is not obvious theorem, but it works because then that especially this a this metric. You choose when you after you change coordinate, the new delta j will depends on the previous delta j. You be careful that this when you change the coordinate, the factors in front can take it out so that this guy can less than this kappa times the gradient. The condition that we added a little bit there. So it's not obvious, but it works. It's good. And also that the orbits of backtracking Newton method for this function capital f and g, if you have a factor in front, this is same. So that's very good. Okay, very good. Then now we can consider backtracking Newton method for this one. So we have this theorem that f be z squared minus 1 on c. So for any of quadratic functions, we reduce to consider this guy. Then if we know this, how the orbit will go for this function, that will be very good. So then for this function, then we'll see that what this theorem tells us that you have this minus 1 and 1. So it says that you take it. So now you see this will be y-axis will be the L for Schroeder theorem. So then you see what the result is. On the left half plane or right half plane. If you're on here, right half plane, then you take any orbits, they will converge to 1. You take this in this side, then all your orbits will go to -1. The difference is when you're on the y-axis, the orbits always converge to 0. This is different with the Schroeder theorem. Okay.
Excuse me, to clarify, so in the backtracking method, you every time you have some freedom, yes? So independently on what you add to the Hessian, you will always have the same picture. This the statement.
Do you mean what's the same picture? What do you mean?
So I assume in general, Bayesian of attraction might, could depend on the parameters on what you add, right? But here it does not depend. Is the statement?
No, yeah, it's because then it's theory said for any of your function f, and delta is you choosing every time you by this author. You always have this result. They always converge to your two roots on two different half plane. The only difference is on the y-axis. It's not chaotic on y-axis. It's contract to this 0, this critical point. Yeah. Okay. So how to prove this is not easy to show. Because why? When you see that how you to prove it? You see this when you calculate this capital F, you get this, and then the gradient is this, hashing is this, hashing is this. Then because we need to calculate WK, right? Because then we iterate Z minus WK, gamma, let's say K plus 1. You iterate this, you need to calculate this WK. But WK, where WK comes? WK is here, you have to calculate the eigenvector and eigenvalues over here. And then you change the sign. If the eigenvalue is negative, to be change it to be positive. So every time you need to calculate the eigenvalues, it's quite difficult to calculate when x and y are both not equal to 0. For example, let's say on the first quadrant. But well, so let's see what's going on first. That's the first case. When x is not equal to 0, y is 0. And the second case is x equal to 0, y is not equal to 0. So this is on y-axis, this is on x-axis. Then these two cases is not difficult to say how the orbits will go, because when your x is not equal to 0, y equal to 0, y equal to 0, then this y is equal to 0, and this guy also equal to 0. Then it's easy to calculate your eigenvalues. Then it's easy to find to say that the WK, how this WK, the vector point which direction. So it's easier to say these two cases. The problem is when you are on the third case, we are on the first quadrant. X and Y both are not equal to 0. How will you prove it? How you say that, let's say on here, any of X, Y in here, how you can prove that this orbit, let's say the 0 is here, and how you can see that later it will contract to here, it's not cross to the other side. It's not easy to show because your X and Y is too much complicated if you do it like this. The reason is it's almost impossible for you to calculate the eigenvalues for this new metric AK. Well, so what to do then? Okay. Now we ask a simple question first. Let's see whether your Z1 can land it on y-axis first. If X and Y both are positive. Well, let's say this one, we figure out this phenomenon on if X and Y both are positive. Then we figure out that this gradient of capital F if you project it to this eigenvector u1 and u2 on the first quadrant, we can see that the red vector is the gradient. So then this gradient is always between this u1 and the u2. It's a very good phenomenon. We use the computer to program, check this. We see this result is very good. Why? Because you know that well, let's see this lemma first. That because you see the projection of the gradient is always positive with a1 u1 plus a2 u2, and the a1 and the a2 both are positive. So then that means that because you remember the wk is always also positive on two direction or two vectors u1 and u2 if you project it. So this means the angle between gradient of f and the wk, they're always between this u1 and u2. So instead of consider this, so then we use this, we choose this u, so net it. So you know, okay, I can draw a little bit here. Let's say this is your u1, u2. So then that maybe your gradient is like this. And you know that your wk is always between this, somewhere between here, because they are always also you change the sign to be positive. So then your wk is somewhere here. So because I cannot calculate wk precisely, so what I do is instead of use wk, what I do is I let it be around here, somewhere here. I choose this vector. Well, it's not easy to well, I should draw it here more. Well, I move it here. Okay, so you net it in like here, some u. So you choose u is this one. Let's suppose you in here. I just move here. Okay, 1 second. With some gradient of f, and then here will be your wk. You're being here, so we net it be here, and then this is your u. You choose this u. Suppose it landed on y-axis. Then if this, okay, you choose this u. And if like this, then your u, this y hat, this one must satisfy this inequality. Okay, very good. Then so then the next step is we need to check this, the function value, whether it's decreased, satisfy this equation. So you see here, instead of use wk in here, we use the capital U in here, the vector u here. Well, then this shows that no, this inequality is not wholes. So this means you will contract to, you cannot land it on y-axis. You're always still on the left half plane. And then the idea is here is it's very difficult to calculate wk, so then you just net it on y-axis. Then you, to simplify, use this vector u, because your wk must be one of your vector u if you choose b1, b2 or properly. It doesn't work here, it shows. But the proof is not finished yet, actually, because they also have another case. It might be cross the y-axis. You still need to go on to prove it. I will not prove it here. So then this is, it will be much more complicated. Even here, you prove this inequality is not easy. You have to be careful to estimate. But thanks to the previous, this y hat has a condition here. So then this one, you can prove it just approximately step by step. And then you calculate, you just assume that Z2 can get causal y-axis to the other side, and then you will say it's not work either. Okay, this is for degree 2. I don't have that much time. I will not talk about the higher degrees. But for higher degree, I can tell you that, yes, the boundary is smooth. Yeah. Okay. I think I just stop here. Thank you very much.
Thank you. Do you have questions? So, as you said, in the case of quadratic polynomial, at least, the basins of attraction do not depend on the step of your method on which delta J, right? Is it true in general? The basis do not depend on the choice interpretation.
No, it's well. The problem is if it's converged globally, then this delta J will give some influence how you choose. Yeah.
I was going to ask you, but I think you answered this with your last sentence, but I'm still going to ask you. So, okay, so what happens in the higher degree? So if you take a polynomial of any degree, this still is the boundary is still smooth?
What's her name?
Yeah, because well, the picture you showed was of a polynomial of degree 3. So did I hear you correctly that you said that this also holds for higher degrees?
3 degree. So looks the experiment result shows the boundary are very smooth.
Okay.
The reason is because they are the stable manifold. Yeah. So need to prove that. Sorry.
Thank you.
Some other questions? No, so let's.